Okay, so this is Rick again, and let's continue where we left off on the last video. We were talking about logarithms. Okay, logarithms are an amazing invention of John Napier from the 17th century, actually 16th century. Napier gave us logarithms along with the lattice method of multiplication and Napier's bones and other really neat mathematical ideas that help us to do things that you might remember, like going to the moon. These are powerful, important mathematical ideas influencing the likes of Johann Kepler, who described planetary motion using mathematics. It's done a lot for us in the field of astronomy and physics. So, where we left off, and this is a key idea. This is one, if you get lost in logarithms, you can always come back to the definition and say that, okay, logs are an exponent. So the log base b of a is equal to c. Okay, you can always take that idea to the bank. Okay, that's an important one. Okay. And from that we were able to say, okay, if logs are an exponent, then b to the c would be equal to log, let's try that again, b to the log base b of a is equal to a. Since b to the c is equal to a, then b to this exponent must also be equal to a. This is a powerful tool, and we'll come back to it more than once. Okay. Also, when we left off, I said, you know, get on your calculator and play around with logs a little bit. I asked, what's 10 to the square root of 2? You should have come up with a number of approximately 25.9546. Okay, so again, if you plug this into your calculator, you know, the decimal expansion goes out. Of course, it's an irrational number, it keeps on going, but you know, it does fit our model because we know 10 to the 1 is equal to 10. We know 10 squared is equal to 100, and so 10 to the square root of 2, since square root of 2 is approximately equal to 1.414, we know that has to fit somewhere in between there. And sure enough, 25, almost 26, is between 10 and 100, so that does fit what we know. Also, we said, okay, we're looking for some exponent on 10 such that 10 to the x equals 5, and we said the way to do that would be to take the log of 5, and if you did that, you should have gotten an answer of 0.69897, which, you know, again, makes sense because we know 10 to the 0 is equal to 1, 10 to the first is equal to 10, so something 10 to some power that equals 5, this x has to be somewhere between 0 and 1. And sure enough, 0.69897, again, this is an approximation only to 5 decimal places, is, you know, meets that definition. It's between 0 and 1, and you know, if you put in your calculator 10 to the 0.69897, you're going to get a value that's approximately 5. You're probably going to be pretty close to the nearest, say, 100,000th, millionth. You know, again, close enough to get you to the moon. The slide rules we saw in the last video did not work quite to that precision, but you know, we don't need, you know, incredible precision to do many things, many of the applications that we would use logarithms for. So with this, let's go ahead and take a look at some of the properties of logarithms. So we're going to look at properties of logarithms. So remember, all these properties are based on the idea that logarithms are exponents. Okay, and that's a key idea here. Think of them as exponents. Okay, so first thing we're going to do, and we kind of waved our hands at this a little bit in the last, but let's go ahead and be explicit about it. I know any logarithm with base 10 is what I call a common logarithm. And since it's common, I don't even need to write the base 10. It's assumed. Just like 10 to the first, we don't write the first, we just write 10. Okay? So I'm just going to write it as log. So the 10 is assumed when I just write log. Okay, this button is on your calculator. Your calculator has all the log tables for base 10 already memorized. Okay, so this is what we call a common log. Anytime I use just log, the base that I'm not writing, there's a little invisible 10 that's right there. Okay, might be a little hard to see. Let's do it in orange. Okay. Okay, so anytime I just write the word log, there's an invisible 10 hanging out there. Okay, so let's look at some things that we know. I know the log of 10 is equal to 1 because 10 to the first equals 10, right? So the log of 10 should be equal to 1 because that's my exponent. The log of 1 should be equal to 0 since 10 to the 0 power is equal to 1, remembering that logarithms are exponents. The log of 0.01 should be equal to a negative 2, since 10 to the negative 2 is equal to 1 over 10 squared, which is 100, which is a decimal, is 0.01. So again, the log is telling me what the exponent is that I need to raise 10 to get my number right here. Okay. So let's play with this a little bit and see where this leads us, because we keep saying logs are exponents. So we know if I have 10 to the x times 10 to the y, then that would lead me to the conclusion of 10 to the x plus y. For example, 10 squared times 10 cubed would give me 10 to the 5th because I'm multiplying a total of 5 tens. Well, let's think about how this would play out in logs. What this is saying is the log of x times y would be equal to the log of x plus the log of y, because logs are exponents. So if I'm multiplying the bases, I'm adding the exponents. Okay, so here the bases are getting multiplied, I'm adding the exponents. Likewise, if I have the log of x over y, then this would mean the log of x minus the log of y. And again, think about what would happen if I had 10 to the x over 10 to the y. Well, to the y, not times y. Well, if I wanted to write this with a base 10, not 1 over 10 something, then I would just subtract the denominator's exponent from the numerator's exponent, and that would give me my new exponent. Could be positive, could be negative, don't know, it depends on what x and y are. But notice how our logs also reflect this very same process. Okay, last idea, okay. Let's look at this one. If I have 10 to the x to the y, I know from my rules of exponents that this is, getting ahead of myself, 10 to the xy. Okay, so notice if I have an exponent to an exponent, I'm going to multiply the exponents. So as this translates into logarithms, the log of x to the y is going to be equal to y times the log of x, because I'm going to take that many exponents to get through. So as we think about this on the order of operations, notice what's happened here. I have taken multiplication and reduced it to addition. I have taken, keep my pen off my tablet, I have taken a power to a power and reduced it to multiplication. Okay, so this is the power of logs. This is what Napier was after when he was inventing this, was finding a way to make multiplication and powers, exponents, so much easier, bringing it down a level. And now what we can do is have a way to do powers of fractions, powers of irrational numbers. We can do all sorts of interesting arithmetical computations that require us to do the things of, such as, computing the moon's orbit around the Earth while the Earth orbits around the sun, and project the trajectory of a space capsule to get from the Earth to the moon. Those are all calculations that require exponents. Well, the logarithms allow us to reduce that into simple matters of addition and multiplication, whereas before we had some really ugly arithmetic to do here that oftentimes would be so daunting that people just didn't do it. And if you look at the history of astronomy, we had some great insights up to the 16th century, 17th century. Once Napier invented the logarithms, you will really see where our discoveries and what we learned about the universe and how the solar system and how things acted really advanced. It really did open the door for some amazing discoveries in the sciences. So that gives us some ways to simplify some things. And again, right now for us it's more of a mathematical interest. There are some things that you will discover in the calculus that logarithms really help us simplify some equations, also in the statistics, that help us break things down into a logarithmic space where it's much easier to work. Things that are exponential in the normal world become linear in the logarithmic space, and it really does simplify lots and lots of things for us. So there was an application for this once upon a time. Anybody over the age of 45 to 50 can tell you about the log tables that they used in high school and college, and slide rules to help them multiply large numbers and to solve exponential equations. It really did have a real practical application. Now it's a little more esoteric with the advent of technology and your amazing little handheld $20 scientific calculators. We've lost a lot of the use for this, but it's still useful from a purely mathematical point. For example, if I'm looking for something, say, I know that 5 to the x cubed is